Okay, hello. Here's the next video about step mathematics. What I'm going to look at today is the first question from the first paper, step paper 1 of 1995. And you see the question on the screen. Question 1, it has 3 parts. Obviously, one very logical way to use this video would be to read this question here and try and do it. So you could pause the video here, have a look at the question, try and solve it. Give yourself about half an hour, up to maybe 1 hour if necessary, and then restart the video and I'll show you my answer and we can compare our approaches. Okay, so from now on I'm going to be showing the answer. Part 1, find the real values of x for which this cubic equation in x is greater than or equal to 0. Now this is an example of a very basic question which, if you've studied A-level maths, which you should have done if you're attempting step, you should find this quite straightforward. You may be a little unfamiliar with solving it as an inequality, but at least you should be familiar with the method to solve it as an equation. So let's look at this first part and then we'll come back. Okay, so the first part, solving the cubic equation. I'm just going to use the bottom part of the screen here because I want to break this down into parts, and I think I'll use this area up here for notes. So there's a couple of things to say. This cubic can be solved very quickly, and the reason it can be solved very quickly is because it has a certain symmetry, which of course most cubics won't. The symmetry here is the relationship between the coefficients of the powers. So the fact that the first coefficient of x cubed is 1 and the coefficient of x squared is minus 4, and then the coefficient of x is minus 1 and the coefficient of x to the 0 is plus 4 is a simple symmetry. Yeah? So you can see a very direct factorization there. The common factor is x minus 4. See, that's x minus 4 times x squared, and that's x minus 4 times minus 1, isn't it? So you can take out the common factor x minus 4 immediately just by observation in that way, and you get x squared minus 1, which trivially factorizes into x minus 4, x plus 1, x minus 1. So that's easy, but I suppose more important is that you should understand, okay, there are always tricks, right? Some people really get obsessed about tricks, but it's not really a good way to learn mathematics as a set of tricks. In a way it is that, but at school level anyway, and even higher. But of course, really you want to learn the most general method possible. And students often ask me, and I'm sure ask other teachers, about the general method to solve the general cubic equation. And the answer is it's quite complicated. I mean, I might do a video about that or something, but it's not something that will be useful to you at school because it's quite complicated and sophisticated, the way that we would solve the general case of the cubic equation. But what I would hope were taught at some point in your education is that there is a trick that allows you to solve some cubic equations in a very efficient way, which is to examine the possible rational roots. I guess I'm going slightly off the topic of the video if I go into it right now, but basically you need to examine the factors of the numbers a and d. So for example, if you had 7x cubed plus, well, let's not use 7, let's use 15x cubed plus 20x squared minus 13x plus plus 6, then what you have to examine is the numbers as possible roots, plus minus 1, plus minus 2, plus minus 3, plus minus 6, these being the factors or possible factors of the number 6, and then also including the possible factors of the number 15 as denominators in a fraction. So you could get something like plus minus 1 over 15 plus minus 2 over 15. Okay, I won't make the whole list, it goes on and on. But if you were taught something like that, that's a very useful trick to know if you're given the problem of solving a cubic equation. It doesn't always work because the roots are not always rational. Well, that's rather large. But it is the kind of knowledge you're expected to have. And the name of this idea, it's called the rational roots theorem. So if you did want to look this up on the internet, suppose Wikipedia, you should be looking for the rational roots theorem. And it's actually quite an easy and instructive exercise to prove this theorem is correct about about polynomial equations. It works for other polynomials, not just cubics. Okay, so as I said, we don't need to use this this method to factorize this polynomial, this cubic given, and hence find its roots, but it's a very useful one to know. So whether you used rational roots or whether you just immediately observe the factorization, it doesn't matter. As you can see here, I'll just sort of highlight it at the bottom of the screen. You can see that taking out the factor x minus 4 gives us the full factorization of the cubic x minus 4, x minus 1, x plus 1, and we're interested in greater than 0. Now, if you're not familiar with how to solve cubic inequalities, the idea is simply this. And I'll just drag this down so you can see. Or maybe I won't, because I want to hide the next part. Sorry, I want to hide the next part. So let me just pause the video and I'll rearrange this. Okay, so done the job there. So understanding this is important for the next part of the question, and of course just generally for your education it's important. There will be a lot of students, especially my own students, who will already know this very well, so this can be just skipped over for them. But if you don't know this, the question is, how can we approach a problem in which we're asked to find the set of values of x for which a product of factors, and I mean linear factors of x, is given to be greater than or less than 0? And one way to understand it is graphically. So you should know, I'm sure almost everyone watching this video knows, that a function like this, so this function x minus 4, x minus 1, x plus 1, has the following shape. And the reason it has these three factors is because each one of those corresponds to a root. If fx is x minus 4, x minus 1, x plus 1, then fx is 0 and x is 4. Okay, here you can see I've already indicated it here. Fx is 0 when x is 4, fx is 0 when x is 1, and fx is 0 when x is minus 1, and we get this shape. So from that, if you know the shape, you can already see for what set of values of x the function is positive. But I hope you can also see that this extends more generally to cases like quartic polynomials. Here's a quartic polynomial: x minus 3, x plus 2, x minus 5, x plus 7. Can you see how we would find the set of values for which this quartic polynomial were greater than 0? So again, you could think of it graphically. If you know the shape is like this, roughly, then you'll understand it. But there's a sort of non-graphical way to understand this, which is critical to this question, which is consider each of these points, these values of x, plus 3, minus 2, plus 5, and minus 7 as critical values. And think about the number line. Sorry, that's supposed to be a straight line. I haven't done this for a while, so I'm a bit inexpert right now. There's a way of change shape to... No, line is not allowed for some reason. Okay, let me try that again. I'm not quite used to this. This is supposed to be a horizontal line. I think I can create a horizontal line. Oh, I need to select it first, of course. Yeah. Okay, does that change to a line? It does. So I suppose that's the number line. And it has these values. Let me just move this down a bit. It has these different values which we obviously need to put in order now. -7, sorry, wrong thing, -7, and then we have -5 is the next one, and then we have, what is it, 3 and 5. And we ask ourselves, where is this function negative? Or rather, we ask ourselves, if x is less than all of these numbers, is the result positive or negative? Well, if x is less than all 4 of these numbers, then we have 4 negative numbers. And 4 negative numbers multiplied together are 2 pairs of 2 negative numbers, obviously giving a positive value. So we know that we've got positive values when x is less than all 4. Now, as we transition from let's say -8 to -6, then we're changing the value of only this factor. Sorry, we're changing the sign of only this factor. The other factors will all change their value, but they won't change their sign, because the value of x going from -8 to -6 will not change the value of x minus 3 or x minus 5 or x plus 2. These will all still be negative. Sorry, these will all still be positive. So we've... Sorry, what am I saying? If sorry, if x is less than -7... Sorry, then yeah, I got it the wrong way around. If x is less than -7, then all of these quantities are positive, aren't they? Because x minus... Sorry, I'm being stupid. X less than -7, they're all negative. If we go over here, then x minus -7, just to be clear, x minus -7, which is x plus 7, now switches to positive, while all the other 3 are still negative. So we've gone from plus to minus by going past this barrier, and then when we go past -5, we switch the sign of this one, so it becomes plus again, minus again, plus again, and we get this obvious repeating pattern, plus alternating pattern, plus minus, as we cross each of the roots. And that corresponds on the graph to these 4 points. In this case, there will be -7, -5, +3, +5. As you cross each of these points, you're crossing the x-axis, because that's what a root is. A root means crossing the x-axis, the place where the function changes from positive to negative. So you get this simple plus minus pattern always for any number of roots. If the number of roots is even, then the extreme ends will be positive, and if the number of roots is odd, the extreme ends will be will change sign. But it has to be said that if there is a repeated root, the pattern changes somewhat. And if you've never thought about that before, think carefully about how that changes the pattern. It's an interesting exercise. Anyway, again, I've gone beyond the scope of the question, but that's especially for people who've never really thought about the solution of polynomial inequalities, because that's what this is, polynomial inequalities. Anyway, after all that discussion, the answer to the first part clearly is that f is positive, the function is positive, only for values of x between plus and -1. Again, look at the shape of this graph. When x is less than -1, all 3 quantities are negative, so it doesn't work. When x is bigger than -1, x plus 1 is positive, these 2 are negative, and it works. And finally, if x is bigger than 4, then all 3 values are positive, all 3 factors are positive, so the function is positive. So the complete solution is f is positive, greater than or equal to 0 for every value of x in the interval between, in the closed interval, I should say, between +1 and -1. That's why these square brackets, meaning closed interval, including the boundary, and also for the set of values between 4 and infinity, including 4. So I hope that part is clear. Let's quickly now look at the second, well, not quickly, but anyway, let's look at the second part of the question. Second part says find the 3 lines in the xy plane on which this cubic polynomial in x and y is equal to 0. Okay, I'm going to pause the video again so I can adjust the position of my answer. Okay, so here's the given equation. I apologise for my messy writing. This is a perennial problem with this tablet. Now, this might be a kind of problem you've never seen before. So that is obviously a critical element of step preparation, is getting used to finding ways to deal with situations you've never seen before. How do we deal with this situation? It's still cubic, but now it's got two variables. So we could write it as f of x and y. That means a function of two variables. Now we want to know when it's 0. And if I remember correctly, the question gives us a bit of a hint. Yeah, because it tells us we're looking for three lines on the plane, xy plane. Now lines, of course, can be written in the form ax plus by equals 0. And notice that ax plus by plus c equals 0 in general. In this case they will be of the form ax plus by equals 0. But you should understand, I hope it's clear, that if we write this general equation of a line, in a way it's something very analogous, very similar to the linear factors that we find in polynomial solutions, or polynomials of one variable. The similarity is that the powers of x and y are 1, yeah? So it's linear in that sense, power 1. In the same way, these have the form ax plus b equals 0. We now have ax plus by plus c equals 0. So those are lines on the plane, aren't they? And so that's actually what we're looking for as possible solutions for this equation in two variables. Even if you've never studied equations in two variables, that's perfectly normal. Don't panic. It doesn't mean that you can't do the question. Alright? So how do you approach it? A few ways, I think, to approach it. Don't be afraid of approaching problems where you're solving equations, of using the method of by inspection. It is another way of saying just look for the answer and find it without a particular method. There are some step questions in which you actually must do this, but whenever there is a by inspection solution, there must almost, I think it's fair to say, there must be a way of doing it logically as well. Now if we look at the first and second parts of the question, we see something of a connection. There's some similarity there. And this is very often the case when they throw something at you that looks new. Double check whether they haven't actually given you a very big hint in the first part. And it certainly looks that way here, doesn't it? Why? Because if we if we examine the coefficients of this cubic, 1, minus 4, minus 1, 4, we've got the same, 1, minus 4, minus 1, 4. Which means that, well, is this really the same problem? Certainly if we substituted y equals 1, we would get the same equation, wouldn't we? Yeah. We would get the same equation. But just substituting y equals 1 clearly won't solve the whole problem, because they're asking us to find lines in the xy plane. You know, if this is a graph, they're saying there's a bunch of lines in this plane that solve this equation. And if we just write y equals 1, then we're only looking at one line on the plane, so that's clearly not going to give the whole solution. So I'll suggest a couple of ways to approach this. The by inspection method, just notice the obvious fact that if y equals x, this equation is true. Do you see that? Because the terms pair off, don't they? That one and that one are the same if y equals x. X cubed minus x cubed, that's 0. And that one, excuse me, also pair off. Minus 4x cubed plus 4x cubed if y equals x. So maybe that's just a case of experience, but for me it was very obvious to notice that y equals x as a solution. But then as a teacher I thought to myself, well, that's all very well. I thought that's all very well, but the student might not notice that. So how else could they do it? I think you should notice maybe that the powers are such that excuse me, dividing by y cubed will also solve the problem. Why does that solve the problem? Because then it becomes x over y cubed minus 4x over y squared minus x over y plus 4 equals 0. And this is a cubic equation we've already solved, because, you know, if you set a new variable z equal to x over y, then z satisfies the same cubic as x did in the first case. And we've already factorized that, so we could just simply substitute it in. So that's probably a very logical, maybe the best way to do it. But and again, it does use the first part of the question. But let's just suppose we went the other way and we said, oh, y equals x is a solution. How could we go from there to solving it entirely? Well, we again use the idea of factorization, and I've already written this out, so I won't write it again, I think. So by observation, if y equals x is a solution, we can use that as a factor. Any solution to an equation is a root. Or any solution to an equation of the form fx equals 0 is a root of fx. And any root can be written as a factor. So the solution y equals x corresponds to the factor x minus y. Now I've written it as x minus y, not y minus x, because we have a plus x at the front here, and I want a positive x power. But actually, I think y minus x would work as well. Yeah, clearly it would just reverse the sign of the other factor. But here we can use what we know about polynomials. We know if we take a linear factor out of a cubic, we get a quadratic factor. Now what form must this quadratic factor take? Well, if we look at the coefficient of x cubed, we see it's 1. So if we have a factor x minus y, it must multiply into a coefficient 1 of x squared, 1x squared there. And if we look at the last term, 4y cubed, and we've got minus y here, then we must have minus 4y squared as the last part. And that only leaves this. Notice here I'm using the same logic that we apply to factorizing just an ordinary cubic. The difference is, and you might get confused by this, that we have this term y, which is actually a variable. But a very, very important principle, and this will help you in many other step questions, is if you have functions of 2 variables, or even more than 2 variables, treat only one of them as a variable and treat the other one as a constant. So here I just imagine that y is a number. It's no different from writing, x cubed minus 4x squared a minus xa squared plus 4a cubed. Students will be less confused by that, even though it's just a different letter, because y is generally considered a variable. But let's treat it as a constant, because for whatever value it takes, well, then we can solve that case for x. And then we'll get x, the solutions for x in terms of y, which will give us what we need. So we see here we simply have a quadratic factor. We already know 2 of the terms. Let's call the coefficient of x b, but noting of course that b will be in terms of y, because y is still held is being held a constant here. And we use the method of equating coefficients. If I look at the coefficient of x squared on both sides of this identity, I see I have minus 4 times y on the left, and on the right I have x squared, b plus b minus y. So b minus y must be the same as minus 4y, so b is minus 3y. So then we have the quadratic factor x squared minus 3yx minus 4y squared must be identical. Well, then just factorize that using normal factorization of a quadratic. How do we factor a quadratic? We either use the formula, or we use the same methods I've just described, for finding factors using a rational roots theorem. Basically, it's kind of obvious. The sum must be 3y, and the difference must the sum must be 3y, and the product must be minus 4y squared. So you've got minus 4y plus y, and that's factorized. Again, we're just treating y as a constant. So now we have 3 factors. What are the 3 factors? X minus y, I'll just write them at the top here. X minus y, that was the first factor we found by observation, or by the more clever method originally considered. X plus y, because x plus y, well, that's here, and then x minus 4y. So this is the factorization of this cubic in x and y, and that corresponds to 3 solutions: y equals x, y equals minus x, and let's say y equals x over 4. And these, of course, are 3 lines on the plane: y equals x, y equals minus x, y equals x over 4. So that's the solution to the second part. Now we'll move on to the third part. Okay, so the third part says, on a sketch, shade the regions of the xy plane for which the given cubic in x and y is greater than or equal to 0. And here's my solution. I apologise for the mess, but I'm not very good at making these drawings. I think it's just about clear enough to see. So we had 3 lines. We knew that on those 3 lines, the value of this function is 0. So all these 3 lines pass through the origin. They're very basic lines on a plane. Y equals x, y equals minus x, and y equals x over 4. Just very briefly indicated them here. And now we use the same principle that I was describing about generally solving polynomial inequalities. Remember that the principle was that as you go along the number line, let's take this this factorization here: x minus y, x plus y, x minus 4y, and let's suppose that y was 2. Then what this would say it would say x minus 2, x. I'll write it as what am I doing? Y is 2, x plus 2. Yeah. So x plus 2 is x minus minus 2. That's x plus 2. And x minus 8 greater than 0. As we said before, as we go along the number line, starting from the extreme left, on the extreme left, extremely negative values of x, such as x is minus 10. All 3 of these will be negative, right? And so the quantity will be negative, so it won't be true. So the 3 points, what would they be? Minus 2, 2, and 8. So on the extreme left, let's say minus 10, we've got a negative value, less than 0. Let's just use a minus sign, that's less confusing. And let's use a different colour. So we've got negative if it's minus 10. As it approaches minus 2, it's still negative, but as it switches over from minus 2 to minus 1, it becomes positive, because one of the factors becomes positive, and then when it switches over here, it becomes negative again, and then when it goes above 8, it's positive up to infinity. Now I hope you can see, well maybe it's obvious now from the diagram, that we can use the same principle here, even though there are 2 variables, because let's just choose one of the distinct regions here. We have they're not very clearly drawn, I apologise. There's a line y equals x over 4 and y equals x, and then another line y equals minus x. Let's take this area here, which I've marked in blue. If we look in that area, let's ask ourselves about these 3 factors: x minus y, x plus y, x minus 4y. If we're in this blue section, notice that we're to the left of the line y equals x. Now, to the left and above of the line y equals x, y minus x will be positive, and therefore x minus y will be negative. So let's use a red mark here. In this area, again, this area that's marked in blue, x minus y is a negative number. And x plus y could also be written as y minus minus x, which is a positive number, and x minus 4y is the negative of 4y minus x, and we're above the line x over 4, so that's also a negative number. So we see we have 3 factors: minus, plus, minus, giving us overall a positive quantity. So that's why I shaded the region here, as requested by the question. I am shading the region where this function is positive, or equal to 0 on the lines, of course. Now you don't have to keep doing this calculation for every region. There's a very simple pattern, isn't there? Because every time we cross over from this region into the next region, and then from hold on, did I make a mistake there? I did make a mistake. Hold on. Yeah, I made a mistake in my drawing there. Let me just pause the video and correct it. Okay, sorry about that slight mistake, but I hope you can see this is the whole point of the question, that as we shift from one region to the other, now this region is the region between the lines y equals minus x and the line y equals x over 4 down here. So then we switch to the next region, which is between the line x over 4 and the line y equals x. Every time we shift between one of those regions, between two of those regions, we change the sign of one of these quantities and one only, meaning that the sign of the final product must also change. So that's why you get this alternating pattern, alternating sign between each of those regions. So there'll be three regions there that are shaded in because they're positive, and three other regions which are not shaded in because they're negative. Okay, so that's the answer to the question. Let me have a quick review note about it. The question is basically about inequalities and basic algebra, by which I mostly mean polynomials. There isn't much else to it. The level of difficulty of the question is definitely on the easy side, but this is very normal for a first question on the first paper. There have been, I think, quite a few questions of this general type over the last several years, usually involving some combination of polynomials, factoring, inequalities, and very often they also use modulus functions. So if you're not familiar with modulus functions, it's definitely worth spending some time on that too. So this was the first question from 1995, and I think I'm going to make several videos covering various questions from the 1995 series, only because I happen to have gone through them all myself last year. So I hope you found it useful, and see you again soon.